Last chapter, chapter 3, we introduced a concept which is called a moment, including three kind of moments, right? Moment of a force about a given point, moment of a force about a given axis, and then the third one, which is, I believe, very important, it's called a moment due to a couple. In reality, in the physical world, you really cannot see two forces following exact definition. But on the other hand, later on when we talk about equivalent force couple system, you see we always use that concept to solve real problems. That's why I believe it's very important. The other application we're going to use is to solve forces acting on the rigid bodies under equilibrium condition. And that is another application from the moment concept. And that's in chapter 4. So we're going to talk about chapter 4 today, which is the equilibrium conditions of rigid bodies. In fact, chapter 3, chapter 4 together is equivalent to chapter 2. Because chapter 2, we simply talk about forces acting on particles, including the resultant force and the equilibrium conditions. In other words, we use Newton's first law already. Chapter 3 and chapter 4 together are the forces acting on rigid bodies and also the equilibrium conditions. The reason we didn't put them together is because this is much more topics we have to cover. So that's why we separate. The book separate. Okay, but keep in mind, this chapter 4 is basically the follow-up from the previous chapter. Okay? Okay. You see there's a lot of problems you cannot solve simply using the concept we learned from chapter 2, because chapter 2 talk about a point or particle only. You typically see those cranes trying to move goods around from one place to another one, but you need to make sure this crane itself is safe. If you are carrying a very heavy load, if you are not very careful to design the support, then maybe you can roll over, right? So that is something we can use this chapter's concept to solve this typical problem. One of the examples are very similar to this one, in fact. Okay? So engineers designing this crane will need to determine the forces that acts on this rigid body. The whole thing is called the rigid body under different loading conditions. Okay? So at the end of the chapter, if you want to come back to review what this kind of things can be solved, at that time you should have a clear idea on solving this type of problem. In this chapter, we're going to split into the material into these two parts again. The first part is called the two-dimensional forces acting on rigid body, and then the second part is three-dimensional forces acting on the the forces acting on three-dimensional rigid bodies. In other words, we call space, and the other one we call the plane. The bottom line is, if we have a rigid body and we see a lot of forces, including moment, acting on the rigid body, we need to calculate the resultant force and calculate the resultant moment. And then if the whole system is under equilibrium condition, that means no movement, then the final resultant force with the summation of all forces must equal 0. And then the final resultant moment with the summation of each moment due to forces together, that's equal 0. So these two are Newton's first law again. The reason this you're very familiar with, this one you may not be familiar with. If you want to argue with me, Newton's first law never talked about moment. At that time, it did not talk about. But on the other hand, towards any extensions, when we deal with the rigid bodies, then this is a very natural extension about Newton's first law, because this allows, there's no rotation for the rigid body. This is no translation, and there's no rotation. Okay? If you want to write these two equations in the component forms, then these three equations are related with this one, having all the x component forces together equals 0, y component together set equals 0, and z component together equals 0. Same thing for the x component moment, y component of the moments, and z component moment, they are all equal 0. So equivalently, this one includes 6 independent equations. Okay? So if you recall what we had in chapter 2, at that time for two-dimensional problem, we always end up with 2 equations. Or three-dimensional problem, we finally end up with 3 equations. Two-dimensional, 2 equations. Three-dimensional problem, 3 equations. However, when we talk about forces acting on rigid body, then actually we have 6 equations for 3-dimensional cases, or 3 equations we're going to focus on later on for 2-dimensional problem. Okay? The bottom line is, again, we just need to know how to calculate resultant force and how to calculate resultant moment at the arbitrary point. So let's first talk about the forces in a plane. So let's take a look about the simplified crane, for example, without considering the truck body. So for example, we have this kind of crane fixed on a certain wall, and then we're trying to use this crane to lift a crate. So when you try to lift a crate, then you need to be careful about these 2 supports. Again, we are going to talk about these supports in the next couple of slides and how to identify those supports. So basically, you see a rigid body like this, and then you need to draw the free body diagram. So we talk about free body diagram in chapter 2 about a point, but this time we need to introduce a free body diagram about the whole rigid body. You plot or draw a rigid body, and then you try to make connections from the rigid body to outside world. So for example, if this is a rigid body, obviously at this point, let's call point A, it is trying to carry a crate. So that don't plot a crate. Instead, you just have an equivalent force acting on here. So this force should be equal to the self-weight of this crate, which is 2,400 kilogram, and then multiply G, because this is not the unit of force. By multiply G, which is 9.81, you're going to have the force unit, which is 23.5 kilonewton. Many times we need to consider the self-weight of this rigid body, and the problem tells you the self-weight is point at G, so then there's going to be another force acting on this point G. It's always going down because of the self-weight. And somewhere they said the self-weight is, well, actually we're going to talk about the example later on. I forgot the exact self-weight, but multiply with 9.81, you get another force in terms of the kilonewton. This rigid body is supported by these 2 illustrations, and in fact point A is called a pin support. We're going to introduce. Pin support means at this point the rigid body cannot move either horizontally or vertically. In other words, you need to provide with 2 equivalent forces when you are trying to represent this reaction or the support. This is a different kind of support, which basically we call the roller, or we call the rocker. The rocker can support in horizontal direction, but it's free in vertical direction. So that's why when you cut here, you only need to provide the support in the horizontal direction. So this whole thing is called the free body diagram on this rigid body. And there's no other forces. Okay, if you look at this original scenario, you consider how this rigid body interact with outside. These are the interactions at point B, point A, point G, and then this may be point H, for example. So this is what we call the free body diagram. With this free body diagram, for 2-dimensional cases, you are going to calculate the resultant force set equals 0. You are going to calculate the resultant moment, and that's set equals 0. And this can be any arbitrary point you want to pick. You can pick point A, you can pick point B, you can pick point this, G, or you can pick point H. It doesn't matter. Of course, we're going to tell you some tricks. Picking a better point, equations become easier. If you pick a very general point, you can still solve the problem. It takes a little bit longer time. Okay, now I want to introduce commonly used support for 2-dimensional problem. And these are what I call the commonly used. So basically, you do need to understand this one and then try to simplify in a more mathematical way by simply putting a force or forces and to represent the support. The first kind of support we can see is called a roller. So roller means you have the wheels. So that means whenever you see the wheels, it indicates in this direction is free, because normally the friction force is very small if you deal with wheels, right? So then like this or this, you can freely move this rigid body, this part of the rigid body, in this horizontal direction. But on the other hand, it's not allowed to move using this support in the vertical direction. So it's not allowed to move in the vertical direction. So that's why these are called rollers. Similarly, there's another name if you see something like this, which is called a rocker. So the rocker, you can see, is kind of a much larger wheel part of this arc, and it's also free to move in the horizontal direction, but it's not allowed to move in the vertical direction. So mathematically, this rocker and the roller are the same. If we want to plot the free body diagram, first you plot this rigid body like this, and then you're going to cut, because this support is connecting the rigid body with the ground. So you have to cut this one. When you cut, you gave a reaction force due to the support. So when you cut here, when you cut here, you cut here, you only gave the reaction in the vertical direction, because not allowed to move in vertical direction, but it's free to move in horizontal direction. That's why you don't have any resistance in horizontal direction. The only force is called reaction is in vertical direction. And this is the force normally we need to calculate based on Newton's equilibrium equations. Sometimes you see this one just having a rigid body at a certain point attached with the foundation directly. Now, if you're seeing this case, you need to look at some kind of descriptions from the problem statement. If they say this is a frictionless surface, if this is a frictionless surface, then at this point the rigid body can still move in the horizontal direction without blocking from moving in the horizontal direction. But it's still not allowed to move in the y direction because there's a support here. So if this is the case and indicate the surface is a frictionless, then this is the same thing with rocker, is also the same thing with roller. No matter what, all these scenarios can be simply use reaction at this point in the vertical direction, but there's no support in horizontal direction. So all this, you can simply use this mathematic to represent. The second type of supports are something like you have this rigid body connected to a wall or foundation through a cable or through a short cable. So you know that the cable force is always along the cable direction. So then if you want to plot the free body diagram about this rigid body, you need to cut here. When you cut here, the force is finally provided by the wall or foundation, but it has to be in this cable line direction. So that's why you cut here, the force is in the same direction with the cable force. Or sometimes we call the short link. Short link is kind of a slender rod. On the other hand, it's only connected from one point with the rigid body, the other point with the wall, and this is called the two-force body, which we are going to introduce later on in this chapter. But the bottom line is, you cut this one, then this force is also along this direction. So either a cable or a short link, when you make the cut, you plot the free body diagram first, plotting the rigid body, and then you need to give a force. It's always along these cable or short link directions. So this is the second kind of support. When we are plotting the free body diagram, you need to give the corresponding force in this direction. Sometimes we see this kind of support. So this is part of the rigid body here. It's supported by this collar. So this typically it is said frictionless rod. This is a frictionless rod. In other words, you shouldn't have any resistance moving in this direction. So if that's the case, the support must be perpendicular to this direction. Because if any force, the reaction, not perpendicular to this, then there's always a component in this direction. Then it's going to violate the statement called the frictionless rod. So if you ever see a frictionless rod, when you plot the rigid body here, and then you cut this one, the force must be perpendicular to this. By the way, it's not perpendicular to this one. This, because this is called the frictionless rod. So when you cut this one, you need to give a force which is perpendicular 90 degrees with this frictionless rod. Otherwise, they always have a components in this direction. It's going to violate the statement. Similarly, if you have a frictionless pin in slot like this, then at this point, the rigid body can move freely in this direction as well, in this slot direction. So then, if you plot a rigid body and then you cut here, then the corresponding reaction or the support must be again perpendicular to this slot. So that's why these two are equivalent to have one force which is perpendicular to this slot direction or the frictionless rod direction. So these are the typical ones. We'll have more on the next slide. Many times we use this, which is called the pin support or called the hinge. So this detailed plotting about a pin or a hinge. But many times, if you look at the book or you look at the question we're going to talk about, it's simply plot like this. So this is also the indicator for pin support. So this is the simplified plot. And this is more detailed plot about pin. Either way, the book use this. Sometimes they use the other one. You call the frictionless pin or a hinge. So when you have the rigid body, this part of rigid body, and you cut this support, then correspondingly, you need to give two reactions this time, because with this pin, it's not allowed to move this point in the vertical direction. It's not allowed to move this rigid body in horizontal direction either. That's how it's the pin. So in other words, you need to give these two reactions, which are equivalent to forces we need to calculate. Sometimes we may say these two forces form one force in a certain direction. These pin support normally allow us to calculate two unknowns, the force in x direction, the force in y direction. But equivalently, you can also plot like this. You say, oh, there's only one force, there's only one unknown. The answer is no. You also need to calculate the angle, because normally we don't know the angle either. So this is the magnitude and also the angle, which means two unknowns, or you just simply plot the two components of this force, which are also two unknowns. So this case is called a pin. And sometimes comparing this one with this, it's almost the same, except they may say the surface of the foundation is a rough surface. If rough surface, that means this point may not be easily moved along this horizontal direction either. Of course, it's not allowed to move in vertical direction. Altogether, it forms two reactions, two forces. One is horizontal, one is vertical. Okay, so this is called a pin, or this is called a rough surface. And finally, we also have a commonly used support, which is called a fixed end support or fixed support. That means this one, the rigid body, not only simply touching on this one, is going into this. If this is the case, it means this rigid body even cannot rotate in this point, at this point. So in other words, this support cannot allow the rigid body move in horizontal direction because it's locked there. It cannot move in vertical direction either. In addition, you even cannot rotate. So if that's the case, then equivalently, when you cut this and look at the free body, rigid body, then you are having equivalent three unknowns. One is a force in horizontal direction, one is a force in vertical direction, but in addition, there's a moment resistance, which we also need to calculate. So this is a moment, but we need to calculate as well. So if we talk about fixed end support, we simply call the fixed support. When you cut this one, you plot the rigid body. Correspondingly, you need to plot these three unknowns. Or you can plot like this. But this is also three unknowns. Two red ones are the magnitude, but you also need to calculate the angle. So that's why this or this is the same when we use a mathematical model to represent a fixed end support. So these are the typical two-dimensional support we have to deal with. And you have to understand whenever we talk about pin or fixed end, we talk about rollers or rockers or short cable or short link and something like this. So you need to know how to use a mathematical model using one force or a couple forces to represent this kind of support when you plot the free body diagram. Okay, so now let's just see how we are going to plot the free body diagram. So again, these six equations or the previous equations, the resultant force equals 0, resultant moment equal to 0, are always based on what we call the free body diagram, just like chapter 2. Chapter 2, when you solve any equilibrium problems, you need to first plot the free body diagram. So normally when we give you a picture, this is not called the free body diagram. Free body diagram means from the picture we were given, we need to identify the rigid body. And once we identify rigid body, we need to plot that rigid body first. And then we're going to see how this rigid body is interacting with outside world. And any interacting should be represented by those forces or by those moments. And that's why I want to use this example to demonstrate how we are going to plot the free body diagram. Once we have a free body diagram, then we can write down those governing equations, the Newton's equations. Three-dimensionally, there are 6 equations. For two-dimensional problems, we have 3 equations to solve any unknowns we're interested. Okay? So back to this one, how are we going to plot the free body diagram? Let's take a look about the original picture. This original picture, you see, this is probably part of the house, for example. This is the beam, and there's a column, and then is having some kind of dead load, self-weight going down. In addition, there's a cable connected through the foundation, and this one, if you see this kind of plot, this is always what we call the fixed end. I forgot to say, if you want to plot the details, this is what we call the fixed end support. But many times, people just simply plot that like this. It also indicates the fixed end support. The frame shown on the left support part of the roof of a smaller building. This one. Your goal is to draw the free body diagram for the frame. The frame means the rigid body. So this blue color stuff is the free body, is a rigid body, or we call the frame. And you may not be sure whether the cable is part of the rigid body or not. We'll study that later, right? So let's first plot this one, and then we look at how this rigid body interact with outside world. First of all, we have these 4 forces. They already gave you 4 forces. That's easy. You just leave those 4 forces. And then you look at this point E. This point E is interacting with the foundation, with this ground. So this point E is called the fixed end. Then we cut this one, and correspondingly we need to give 3 forces, which are 2 real forces and a moment force, or we call a moment restriction. Okay, so at this point, later on, we need to plot 2 forces, horizontal, vertically, and also the resistant moment. Now, this rigid body is interacting with this ground through this cable. So it's up to us how we're going to cut. We can cut here, or we can cut here to isolate this rigid body from outside world. You cut here, then you give a force along the cable direction. Where you cut here, you also give a force in certain direction, along the cable direction. So this essentially is something like this. Okay? Finally, you may say, do I need to cut between B and D? Well, point B and point D are both part of rigid body. There's really no need to cut, because this rigid body in these 2 locations are not really interacting with outside world, because this B is in the air, this point D is in the air, and this cable in between, that's just part of the cable. You really do not need to cut. Some problems, if somewhere in between they connect with outside support, then you need to make the cut, but not this case. So typically, we do not need to cut between point B and point D. If you really want to cut, that's not a problem. You cut in here, you give a force in this direction, you also give force in other direction. These 2 forces are always canceling each other. So with this kind of explanation, let me show you what is the rigid body, free body diagram we're supposed to plot. Okay, so let's take a look at point A, point B, the different scenarios, right? Is this a real free body diagram, or is this a real free body diagram, or this, or this? Let's take a look and to decide which one is correct or which one is not correct. Let's take a look at the case A. So again, this is the original picture I just copied from the previous slides. This is the original picture. We first plot the rigid body, and we have 4 forces acting here. This is a fixed end. When we cut this, we gave 2 reactions and 1 moment reaction, right? So this is what I just explained to you. Now, this case A, somebody just cut here and then gave a cable force in this direction. And that's not correct. The reason this is not correct because when you cut this one, it's not a problem. You give a force in this direction, it's not a problem. But this one is not connected with outside world directly. It's through this point D. So when you cut this one, you also need to give another force in this direction. Something like this, for example. So when you cut this one, you need to plot these 2 forces. Don't worry about the magnitude. Actually, the problem does give you the magnitude, but we're talking about this concept of the free body diagram. We don't need to worry about the magnitude. So if you plot this one, that's okay. And then you still need to cut with a foundation. And this case it doesn't do that. So that's why this is not correct. In other words, this is not the correct free body diagram. And then let's look at case C. Case C, as I explained to you, if you cut this one, it's not a problem. You gave these two forces, but in the opposite direction, they are always canceling each other. And then they further cut this one so that this whole thing is isolated from the foundation. Then when you cut this one, you need to give a force. And again, at point E, you cut this one, is a fixed end, then you give these three. So in reality, this is correct. So case C is correct. But case A is not correct. Now, let's go back to look at case B. If somebody wants to plot the free body diagram based on the rigid body still here, and then gave 4 forces at point E, again 3 supports, not a problem, and they only cut just somewhere here. When you cut this one, again you gave the force going down in the same direction, cable direction. That's also fine. It doesn't really matter you want to cut here or cut here or cut here, it doesn't matter. As long as you gave the force in the cable direction. So you may say, well, this person doesn't cut this. You don't need to cut this one. The reason you don't need to cut this is simply because both point B and point D are part of the rigid body. There's really no need to cut. And between B and D, there's no connection to outside. That's why you don't need to cut. And this is also correct. Finally, let's come back to case D. Case D, they consider the entire frame and the cable as a rigid body. That's not a problem either. You gave 4 forces here, and then this fixed end, you cut point E, then you gave 2 reactions, horizontal, vertical, plus a moment resistance, no problem. But then you did not cut this. Then this is never called a free body diagram. Because free body diagram is to show a rigid body and all connections to outside using forces or using moment. This one you did not cut, then basically you are considering part of the foundation as the rigid body, a free body diagram, the rigid body. That's not right. So definitely, anytime when you see the rigid body interacting with the foundation or wall, you must make the cut. It doesn't matter where you're going to cut, but you must make the cut. Yes?
Why isn't there a force acting on C? Isn't C supporting the...
Okay, good question. You see, all these 4 cases, we didn't touch on this point C. Why we don't need to cut? Because point C is part of the rigid body. If point C is connected to outside, then you have to make the cut. You may say, well, this point C is connecting this part of the beam with the column. But keep in mind, we are assuming both the beam and the column together as a rigid body. So that's why there's really no need to make any cut, point C. If this point C, say, okay, point C is connected with a real wall or a foundation, vertical foundation like this through a pin or something, then you have to make the cut. But this one doesn't have anything there. So that's why you don't need to make the cut. Any other questions? Okay, so the first step is to identify so-called the rigid body. Once we can identify the rigid body, then we will see how this rigid body is interacting with outside world. And we don't want to bring the outside world as part of rigid body, but we need to use the forces. We use the moment to simulate that connection. For example, like point E, this rigid body is interacting with the outside world, which is called the foundation, through what we call the fixed end. That's why you cut this one, you gave these forces to simulate the connection, the interaction to the foundation. At point F or at point D, when you make the cut, this is the interaction through the cable direction. So that's why you need to give the force, this or this. This one. But the bottom line is case A is not correct. It's simply because you cut between B and D, but if you cut this one, you need to give another force at point D in the vertical, in the opposite direction. You didn't do that, that's why this is wrong. This one, it is wrong, it's simply because you are still considering part of the foundation as the rigid body. That's not correct. So B is the most correct. Well, is it correct? Although C is also correct. So these two are both correct, but A and D are wrong. If you say which one is better, well, obviously this is better because you don't have a lot of forces right? You compare 1, 2, 3, 4, 5, 6, 7, and 8. And this one additionally have 10. The reason you plot these two forces, that's really redundant because they're always canceling each other. So that's why you don't need to plot this. Then you say, well, if I do not need to plot, do I still need to write the cable here or not? It doesn't matter because normally we do not consider the self-weight of the cable. Comparing the self-weight of cable versus the whole rigid body, the self-weight can be neglected. Okay? Okay. Now we are trying to let you know how to establish those equilibrium equations for two-dimensional problem. For example, we have this another truss or frame, you can call whatever you like. For two-dimensional problem, there are three forces acting like this way. It's supported as a pin at point A and also a roller at point B. So first of all, we do need to plot the free body diagram. So you just redraw the rigid body. And at point A, it's connected to the outside foundation. Cut in here, you gave two reactions. At point B, is a roller. You cut here, you only gave this vertical force. There's no horizontal because it's free. It's the wheels. And then you normally need to consider self-weight of the rigid body. And then you say, okay, self-weight is going down always. And then you have three applied forces. You plot the three real forces. They did not plot this directly, but instead they gave you the two components for each force. That's also fine. Or you can just plot like this. So this is what we call the free body diagram for this rigid body problem. For any two-dimensional problem, we basically have three equations based on the resultant force together equal to 0 and the resultant moment together equal to 0. So how are we going to specifically write down those governing equations? There are many ways you can write down those governing equations or equilibrium equations. But keep in mind, there are only three independent equilibrium equations. Okay? So it's up to you how you're going to pick three equations out of the group. Many times, most of the time, this is the three equations I always use. First of all, you just need to collect all the x component of forces and add them together equal to 0. So this is the resultant force equal to 0 in terms of x direction. So for example, like this one, you just collect all the forces in this direction. You have this one, you have this one, you have this one, you have this one. You add all these four components together equal to 0. That's the first equation. Second equation, you need to collect all y component of forces, add them together equal to 0. For example, like this, you then need to have this, and add them together equal to 0. That's the second equation. So these are the two force equations. The third equation should come from a moment contribution. In other words, you need to collect the moment at any arbitrary point. So this point A is any point. In other words, you can pick point A and you collect the moment of all forces at point A and set equal 0. Or you can pick point B, or you can pick point D, you can pick point G, you can pick, where's this point? Point C, any point you like. It's not a problem. The bottom line is you want to pick a point so that the corresponding moment equation is as simple as possible. What does that mean is, if you pick point A, then these two unknowns will not be involved in the moment equation. So that's why normally we want to pick a point with unknown forces acting on that point. So that you have unknown AX, you have unknown AY. These two unknown forces will not be involved in this equation. In other words, you only have one unknown, which is called B, will be involved in this equation. Just from this one equation, you can calculate B directly. If you are picking this point, then this force, you have a moment of this force about this point involved in this equation. You have the moment of this force about this point in that equation. You have the moment of this force about this point also involving this equation. It's really nothing wrong, but this equation itself has to be combined with other equations in order to finally solve these unknowns. So that's why one trick is to pick a point with more unknown forces acting at that point. And that's an easier equation for us to solve any unknowns we have to. Any questions? As somebody raise your hand. Okay, so, sometimes You may say, well, I don't like to pick 2 force equations and 1 moment equation. Can I choose something else? For example, I just want to choose 1 force equation. In other words, I'm interested in collecting all the x component of forces together equals 0. Not a problem, because this is the same with this one. And then I'm going to pick a point and to collect the moment of forces about this point equal to 0. And then can I pick another point, point B, and then I'm going to collect all the moment of forces at this point and set equals 0. It's not a problem. So these 3 together are also forming the 3 common equations. Okay? So it's a matter how you're going to pick those points. So you combine these 3 equations to solve for these 3 unknowns. But most of problems, you can easily just use this one to solve typical 2-dimensional problem. Sometimes when you use this, you can make the problem solve a little bit more faster. But in general, if you just want to make it more unified way, this is the typical 3 equations I normally use to solve any 2-dimensional problem. You may say, what are the other 3 equations? All the other 3 equations are trivial equations or redundant equations. Okay? For example, do I need to collect all the forces in z components and add them together equals 0? There's no need, because this is a trivial equation. 2-dimensional problem, there's never has any z component. Okay? In other words, do you need to look at any arbitrary point and then using the vector form to calculate x component of the moment, y component of the moment, add them together equals 0? You don't need. These 2 are trivial equations because there's no such moment in x and y component for 2-dimensional problem. It's only one component which is in z direction. So that's why this or this or this, in fact, all in z direction. Then you may say, can I pick 3 points and then I can calculate the moment of forces at point A equals 0, point B equals 0, point C equals 0? It's not a problem either. You can pick those 3 points and then establish moment equations. Then you say, well, if I really have more than 3 unknowns, can I pick 4 points and write down all the moment equations on those 4 points? Among those 4 moment equations, only 3 of them are independent from each other. So that's why you can pick many points. You say, I pick point C, I pick point D, point B, point A. Can I correspondingly write down all these moment equations? You can write those equations down, but there are only 3 independent equations. The more equations you're going to write, it doesn't help you out, in fact.